So, in the last session, we learned about measurement of length and volume. Now, in the concluding part of this chapter, we will talk about measurement of time and of mass. What is time actually? It's a very interesting quantity. Normally we think time is absolute, but it is not. If you think about Einstein's theory of relativity, it says that if there's a clock attached to a body and that body is moving with a very high speed, let us say 20% of the speed of light, then that clock on that body will slow down. The time is not absolute, it is relative. But that is a very advanced concept. We will not talk about that. But even then, is time absolute? What is measurement of time? If you look at your watch and you say it is 11 o'clock, is it 11 o'clock? For you it is 11 o'clock. For a person in Singapore, it would be 1:30 p.m. at the same instant. And for somebody in New York, it may be 1:30 a.m. at the same instant. So different people are giving different versions of time. They are all right, they are all correct, because we have time zones and we have divided the day in 24 hours. All that is correct, it is scientific. When we talk of measurement of time, we are actually talking of measurement of a time interval. For example, you want to measure how much time is taken by a sprinter to run a 100-meter race. When he starts, exactly at that instant you start a clock. And when he touches the finishing line, you stop the clock. And then in the clock you see the reading of the time interval between two events, the start of the run and the end of the run. So that is a time interval we are talking about. We can measure this interval with a stopwatch. One is a traditional stopwatch, other is a digital stopwatch. Traditional is analog. Here you can see that there is a dial which is measuring seconds. This hand will move and it has got divisions. You can see here this is 5 seconds, this is 1, 2, 3, 4, and in between there is another division. So the smallest division is half second, and that is the least count. Least count of an instrument is the smallest division on that instrument. So when you want to start measuring, you press this one. The second hand starts moving. Tick, tick, tick. If it covers more than 1 minute, then this is the minute hand. This will advance by 1. Like that, let the clock keep going on, and when the event ends, then you press this once again, the clock would stop, and then you can read the time interval. With this lever you can reset it, that is, come back to the 0, 0 situation. Usually the least count in such stopwatches is 0.5 seconds. In a digital stopwatch, the least count can be much smaller than that. 1/10 of a second, 1,000th of a second, and so on. Now this is a very interesting device to measure the time interval, and that is with the help of a pendulum. So here I have a pendulum. What is a pendulum? A small heavy bob tied to a string which is light and inextensible. Now in this position it is in equilibrium at rest, and it will be vertical because the weight of this bob is acting downwards. It is at rest, so there is an equal and opposite force, namely the tension in the string. That is why it is at rest. That is called the mean position or equilibrium. If I disturb it from the equilibrium and then release, then the net force on this is not 0, and it will oscillate like this. You can see in the animation there is an oscillation going on. Oscillation is a periodic motion. What is periodic motion? A motion that repeats itself. And whatever gets repeated is called a cycle. In this animation, what is one cycle? Cycle means you are back at the same point from where you started with the same velocity. So you can start measuring from any point. Suppose I start measuring it from the left extremity. That is when I start. Alright, so it goes this side and comes back. It is back at the same point from where it started with the same velocity, which was 0. That is one cycle. We can start from here also, from the right extremity. So it will go to the left and then come back. That is one cycle. And that cycle repeats. Suppose we start at the mean position here when the bob is going to the right. Alright. So it goes to the right and comes back to the mean position. Is that one cycle? It is not. It is only half a cycle. Because although it is at the same position, but it has got an opposite velocity. So we need to wait, let it go this side and come back. Now the velocity is again to the right. So the cycle would be to go from here to here, then to the left extremity and then back. That is one cycle. Now, let us define some terms. One is the amplitude. Amplitude is a maximum displacement from the equilibrium or mean position. In this case, it is an angular displacement. So the maximum deviation is this much, and this is the angle from the mean position. Let's call that theta naught. So theta naught is the amplitude. It is an angular displacement. In some cases it may be a linear displacement. We just use the word displacement. Oscillation is a periodic motion that repeats itself. Every capital T seconds. What is capital T? The time period, meaning the time taken to complete one cycle or one oscillation. What is frequency? Frequency is the number of cycles per second that will be the reciprocal of the time period. Now, how do we arrive at this relationship between frequency and time period? Suppose the time period is 0.1 second. Then it takes 0.1 second for the first cycle, 0.2 second for the second cycle, 0.3 second for the third cycle. Like that, we can fit 10 cycles in 1 second. We can fit 10 cycles in 1 second. That means it does 10 cycles in 1 second. That is the frequency. It is measured in hertz. Frequency would be per second. The SI unit is called hertz, named after the scientist Hertz, written as capital H and small z. Now, this pendulum can be used as a clock, but first we need to find out the time period of this pendulum. Once we know the time period of this pendulum, then we can use the pendulum as a clock. And how do we measure the time period? We let it oscillate for many times, not just once, maybe 10 times, maybe 100 times. Let it make n oscillations. And then you measure the time using a standard stopwatch. Let the time taken for n oscillations be small t. Then the time period is small t upon n, because time period is the time taken for one oscillation. For example, if it takes, let's say, 200 seconds for 100 oscillations, that is small t. 200 seconds is small t, the time taken for 100 oscillations. So for each oscillation, how much time is taken? The time t, that is 200 seconds, divided by n, 100, that is 2 seconds, is the time period. Now the time period has got a relationship with the length of the pendulum. The length of the pendulum is a distance between the center of gravity of the bob and the suspension point. So this is the suspension point, this is the bob, it is spherical here, and this is the center of gravity. So this L is the length. The bob should be small and heavy. Heavy because we want a sufficient tension in the string, and it should be small. If it is too big a bob, then some other considerations come in. We are not going to talk of those considerations right now. So given this, the time period has got a relationship with the length in this manner. The time period is proportional to square root of the length. It is not a linear relationship. So suppose you have an equation connecting y and x, y is equal to some constant a into root x, then it will be a curve like this. It won't be a straight line. Now, what is the exact expression for the time period? There is another quantity on which the time period depends, namely the acceleration due to gravity small g. That has got a value 9.81 meters per second square. The value of g varies slightly from place to place, but at a particular place it will be constant. So we say that the value of g is temporally constant but spatially variant. Temporally constant means it doesn't vary with time, but it varies with position. So if you're doing an experiment at a particular place, the value of g will be constant, and that is why we say that the time period is proportional to root L, because we can write time period as 2 pi upon root g into root L. So time period, this is a constant. The time period is proportional to root L. If you plot time period versus the length, then as we saw, it will be a curve. But if you plot it versus root L, then it will be a straight line passing through the origin. This equation is of the type y is equal to mx. This is the equation of a straight line passing through the origin with the slope m. What is the slope? If this is theta, then the slope is tan of the angle. So here the slope is 2 pi by root g. Suppose you square it up, then t square will be equal to 4 pi square upon g into L. Now 4 pi square upon g is a constant, and then the slope becomes 4 pi square upon g. There are some interesting dependencies here. As we saw, the time period depends on L not linearly, but we know that larger the L, larger the time period. But it's not a linear relationship. Namely, if you double the length from L to 2L, what happens to the time period? It doesn't become 2 times. It becomes root 2 times. Why? I will say time period is some constant into root L. Initially the time period was this. What is the new time period? T dashed is equal to the same constant into root of the new length, which is 2L. I can take this root 2 outside, then you can see that this quantity is the old time period. So the new time period is root 2 times the old time period. If you double the length, the time period doesn't double, it only becomes root 2 times. Now, one very interesting experiment you might have done. You have been on a swing. The swing has got a certain length. What is that length? The distance from the suspension point to the center of gravity of the bob. Now you are the bob. You plus the chair totally comprise the bob, and that bob has a certain center of mass. Based on that length, there will be a certain time period. If you stand up, your center of gravity goes up. The combined center of gravity of you and the chair also goes up. That means the length of the pendulum reduces. The time period reduces. frequency increases because frequency is a reciprocal of the time period. That means it does more cycles per second. That means it oscillates faster. If you stand up on a swing, you will find you are now oscillating faster. Another interesting thing is, there are pendulum clocks where it is a rod-based pendulum. That is, instead of a string, there's a metallic rod. Now you know that things expand on heating and contract on cooling. So the whole pendulum clock is calibrated at a certain temperature. During summer the temperature goes up, so the length of the pendulum goes up and the time period goes up. The pendulum slows down, the clock slows down. It takes more time to complete one oscillation. And during winter it contracts, the length reduces, the time period reduces. Let's understand this part. During summer, why does the clock slow down? Now in all those clocks, the method is usually that when the bob goes through the midpoint, whenever it goes through the midpoint, then the second hand moves by 1. So suppose it is calibrated properly, the time period is correct. Now during summer the time period increases. So earlier suppose it was taking 1 second, now it is taking say 1.5 seconds. So it takes 1.5 seconds now to do an oscillation, but it shows only 1 second because the movement of the second hand is based on when it is crossing the mean position. So it is taking 1.5 seconds but showing only 1 second. Correct? So the actual time elapsed is 1.5 seconds, but it is showing only 1 second. Similarly, an actual time elapsed maybe 1.5 hours, but it will show only 1 hour. So suppose you start at 8 a.m., you match that pendulum with a standard watch, and then let that pendulum oscillate for a certain time interval. Now that pendulum clock, suppose it shows 9 a.m. 8 a.m. you started correctly. Now the pendulum clock is telling you it is 9 a.m. Is the time 9 a.m.? No, it is 9:30 because it is showing only 1 hour but taking 1.5 hours. So it has slowed down. The time was 9:30 but it is showing only 9. The clock has slowed down. Likewise in winter it will speed up. What about G? The time period does depend on G. It is inversely proportional to the square root of G. If G is larger, then time period will be smaller. Now G does vary slightly from place to place. If you take a pendulum atop a mountain or inside a coal mine, in both cases the value of G reduces and the time period increases slightly. On the moon, the value of G, acceleration due to gravity, is only 1/6 that on Earth. So if you take a pendulum which had a certain time period on Earth and you take it to the moon, the time period on the moon will be larger because the G has reduced. If you reduce the G, the time period would increase. That's what happens. But not 6 times. There's a square root here. Okay. What about the mass of the bob? The mass of the bob doesn't have any impact on time period as long as the bob is small in volume. And does it depend on the material of the bob? No, it doesn't depend. Does it depend on the amplitude? No, that's a little bit of tricky question. Amplitude. See, this is a small amplitude. Okay, and this is a larger amplitude. The time period does not depend on the amplitude as long as the amplitude is small, say 10 degrees, 5 degrees. But if it becomes larger, then the time period does increase. So we generally say that amplitude is kept small, so the time period doesn't vary based on the variation of amplitude. So the time period of a pendulum only depends on the length of the pendulum and the value of the small g. Seconds pendulum is a pendulum that has got a time period of 2 seconds. And this is the arrangement. You can see here that our pendulum is this. It is oscillating. Now look at the vertical rod. It is oscillating to and fro. See here, whenever it crosses the mean position, this yellow wheel rotates by one angle. The second hand moves. See here, ready? 1, 2, 3. 1, 2, 3. So when the rod goes like this or like this, the yellow wheel is turning by a given angle. That is the second thing. So each time the pendulum rod passes through the mean position, the second hand ticks each time. So the pendulum is going from here. When it crosses this point, the second hand moves. That means 1 second. Again, when it comes back, another 1 second. So the time period of this pendulum is 2 seconds. The time period of a second's pendulum is 2 seconds. Correct? Now let's talk of measurement of mass. What is mass? Mass is also a very interesting quantity. At this level, I would only say that mass is the quantity of matter contained in a body. But as you go into higher classes, you will see finer definitions of mass, finer descriptions of mass. One you would learn is that mass decides the inertia, that is, how much speed it will get if a certain impulse is given to the body. Mass is that property which decides how much speed it will get. For a given impulse, a small mass will obtain a larger speed, and a larger mass will have a smaller speed. Going even higher, Einstein said that mass is actually a condensed form of energy. Those are advanced concepts. At this level, let's treat mass as the quantity of matter contained in a body. Because of the mass on Earth, it will have a weight, and the weight depends on the mass. Larger the mass, larger the weight. How do we measure? Using this kind of a scale. You might have seen vegetable vendors using this. So how do they measure? If you want to buy 2 kg of potatoes, they will put a certain block and they say that this is actually 2 kg, a standard 2 kg iron block. And then they will put potatoes on the other one. If there are too many potatoes, then the right side will dip. If there are too few potatoes, then the left side will go like this. And if the number of potatoes is exactly same, that is, the mass of potatoes is exactly 2 kg, 2 kg here, 2 kg here, then this beam would be horizontal. Another kind of a scale is this, where you're buying apples, you'll keep a standard known mass over here, and when the two masses are equal, then this pointer that you see will be perfectly aligned with this one. This works on the principle of moments. What is a moment of a force? First of all, force itself is something that causes a body to move or changes the speed or direction of a body which is actually and already moving. That is what is force. What is moment of a force? Moment is also called torque. It is a vector quantity, and this torque makes the thing rotate. So, if you look at a scale, all the scales are such that they can rotate about this point, which is the center of this beam. It can rotate, it can become like this, it can rotate like this, or it can become like this. The midpoint, which is pivoted, is the axis. The axis passes to that point. So when you have a torque or the moment, it causes rotation. Torque is a vector, so direction will indicate by clockwise or anti-clockwise. What is moment? Let's understand that. Suppose there's a beam like this and I apply a force by connecting a mass, it has got a weight W. The weight is a force, it's a vector, it acts downwards. This will make the whole thing rotate anti-clockwise. If I put an equal weight on this side, then this will be horizontal and balanced, it won't be rotating because this weight is now exerting a clockwise moment of the same magnitude, opposite direction. Those two torques cancel out and hence no rotation. Important that this length must be equal to this length. So moment of a force is the force into the perpendicular distance. This is the force. The line of action of this force is this. The perpendicular distance from the axis is, let's say, d. Then the torque is equal to the force, that is the weight, into d. That is the magnitude, and the direction for this is anti-clockwise. For this guy, this is the line of action of the force and it is at the same distance. So the torque exerted by this is also the same in magnitude but opposite in direction. That is called the principle of moments. In the lab, you are going to use a much more sophisticated scale like this. Same principle. We have a beam. We have two pans. We put a known mass and the unknown mass will be placed here so that we can balance and then see what is the mass of this. So how it works is like this. This lever, when it is down, then this beam is resting on this. Whatever weights you may put, even if those two are unequal, the beam would not shift, would not rotate about this axis because it is already resting. Now with this, if you now turn the lever, then the beam rises up. And if the two weights are different, if the two masses are different, then the beam would be either like this or like this. And that is indicated by this pointer which is pointing down at the scale. So suppose the left side is having a larger mass than the right hand side. So the beam, instead of being like this, will become like this, and the pointer would point like this. Larger the difference between the two masses, larger would be the deviation of the pointer from the mean position. So to balance now, how do we use it? Now, this is the unknown mass that we want to measure, okay? So we put a known mass, say we put 50 grams over here, and then we find that the beam is like this. That means that 50 grams is too much. The mass of the unknown object here is less than 50. So you remove this and replace it with a smaller mass, say 20 grams. Again you find that the beam is tilted, but now it will be less tilted. The pointer will be pointing somewhere here, indicating that the difference in the two masses, the difference between the two masses has reduced. So now you replace 20 with 15, like that, and ultimately you get a balance. Very important that the whole system is horizontal. And you check that with this spirit level, which contains a liquid and a single bubble there. If it is perfectly horizontal, this bubble would be right at the center, otherwise not. So if it is not, then you use these leveling screws over here to make it horizontal. This beam balance also works on the principle of moments. So what we are doing is, we are measuring an unknown mass by comparing it with a known mass. So what are the precautions? The lever should be turned gently so as to prevent the chipping of knife edges. There are knife edges on which the beam is sitting. You don't want to damage it. When you want to add or remove masses, You see, the unknown mass is resting on one pan. You don't disturb that. You are changing, adding or removing masses on the other one. So whenever you do that, you lower the beam so that it rests on the support, and then you add or remove and then again lift the lever up. The weights are very small. They should be carried with forceps because moisture and dust can change the weight. There's a weight box that contains standard masses like 10, 20, etc., 500 milligram. This is 10 milligram, very small. Or it can go all the way up to 500 grams. So you can get various kinds of denominations by using combinations. So you start your experiment by putting the object on one pan. You have an estimate that this may be, say, 50 grams. Just by looking at it, you don't know, you want to measure. So you put 50 gram, a known 50 gram mass on this one, and then you lift the lever. Suppose you find that the beam is like this, that means this is heavier, 50 gram is too small. Then you add a 20 gram. Suppose now it becomes like this. That means now this is too much. So that means the mass of this unknown object is between 50 and 70. So you remove the 20, you know that it is more than 50, and now you are going to approach the actual mass of the unknown object. So now you add weights in descending order because now you are making it finer and finer and finer. Slowly you are reaching. So you add 10, and then you add 5, and then you add 2 grams, or let's say milligrams, until you get the exact balance. Means the pointer would be directly vertical. This is an important principle. Near the actual weight, the weight should be tried in descending order. Wet and hot objects should not be kept in the pan, and the weights should be replaced in the weight box after use. The conditions for a true balance: both arms should be of equal length. That is very important. You see, we have a beam. This is the axis. This arm, both must have the same length, so that during balance this weight and this weight are equal. If these two arms are of unequal length, then at balance these two weights will also be unequal. Suppose I call this D1 and D2. They are not equal, and W1 and W2 are the two weights, and we find that the beam is horizontal. Then by the principle of moments, the anti-clockwise moment due to weight W1 is W1 D1 about the axis, and W2 D2. Since D1 is not equal to D2, W1 is also not equal to W2. That is why both arms should be of the equal length, and both pans must be of the same weight, obviously, because we don't want an error coming due to the unequal weights of the two pans themselves. So let us conclude this by doing some questions on pendulum, and these are from the ICSE textbook. What is the length of a seconds pendulum? The G value is 9.8 meter per second square at that place. So the time period of a seconds pendulum is 2 seconds. T is 2 seconds. This is the expression for T. Square it up. Write the expression for L. Square it up means T square into G divided by 2 pi. G 9.8. Time period is very important for a seconds pendulum. 2 seconds. 4 pi square, we get 0.994 meter, nearly 1 meter. So the length of a seconds pendulum is nearly 1 meter. Next, compare the time periods of two simple pendulums of lengths 1 meter and 16 meter at a given place. So comparison means taking a ratio. G is the same because we are doing the experiment at a given place. So we simply use time period being proportional to root L. So T1 by T2 would be equal to root L1 by L2. L1 is 1 meter, and L2 is 60 meters, so this is 1 by 4. T1 by T2 is 1 by 4. That is the ratio of the two time periods. We know G on Earth is 9.8 meter per second square, and we know that G on Moon is 1/6 that on Earth. Compare the time period of a given pendulum. Now the length is the same, but the G is different. So the time period is inversely proportional to the square root of G. The length is the same. So time period on Earth divided by time period on Moon. Because of this relationship, it will become root of G on Moon divided by the G on Earth. Now G on Moon is 1/6 G on Earth. So G on Earth cancels, it is root 1 by 6. It is not 6 times or 1 by 6 times, it is 1 by root 6. That is the ratio. Time period on Earth divided by the time period on Moon. The time period on Moon will be larger because G has reduced. What will happen to the time period if the bob is replaced by a heavier one? Mass of the bob doesn't matter as long as the bob is small in volume. Only the length matters, and of course the value of G. So that completes this chapter. Please do the assignment which is there within the course material.